Welcome back, everyone, for another episode of IGCSE Math ZNotes Live. My name is Devandhira, and I'm your host for this episode, along with our expert, Ivan Zelich. So, Ivan, please introduce yourself.
Thanks, Devan. Welcome back, everyone, to another lesson of IGCSE Math. So, for those of you who might have missed the previous lessons and who are just tuning in right now, my name is Ivan. I am a master's student at the University of Cambridge, and today we're going to go through trigonometry. So, as usual, without further ado, let's get into it. So the key concepts for today, well, it's basically trigonometry, but trigonometry can have many different kind of sub-areas like bearings. And trigonometry, obviously, you can apply it to geometric situations. So, things that we were doing before, we'll see again, but asking different types of questions, like finding precise lengths, which in some sense we hadn't had done in the previous lessons. Right, Devan? Like, we did some angles and stuff, and maybe area, but it was hard to calculate lengths unless we had a right angle triangle.
Yep, that's correct.
So that's what we'll be doing really today. Right. So bearings. So a bearing from a point to another of a point from another point is an angle measured from the north in a clockwise direction. So that's the bearing. So from north, clockwise is the bearing of B from A. Alternatively, you could also ask the angle of depression, and that would be from B horizontally to A. But also you could ask for the bearing, in which case you'd have to go all the way across for a clockwise direction. So you could be asked different types of questions, and remember, bearing is the one from north clockwise. And yeah, it's written as a 3-digit figure from 0 to 360. And yeah, I guess it's useful to just talk about why this is 205. Basically, if we imagine we shift this north, because we have some parallel lines, actually we don't have to do that. We have some co-interior angles here, 25 and 180 minus 25. And then this is 360 minus 180 minus 25, which is 180 plus 25, i.e. 205. Okay, Pythagoras' theorem. I mean, we've used this so many times, but let's just say that there is actually quite a nice proof of Pythagoras' theorem. So basically, the triangle, this ABC triangle here, we have the triangle right here. So this is the triangle ABC. And basically, the point is that B squared here and A squared here, these are squared. And the rest we have some that fill up C squared. And so basically we want to prove that A squared plus B squared, these areas, is equal to C squared. But this length of this square, sorry, I said C squared, but I meant A plus B. And then we can rearrange these kind of shapes and get this shape here. And what we end up doing is we get a little square here. Well, not a little square, quite a big square. You can see is the longest side. And basically, it means that this area plus this area equals this area, or A squared plus B squared equals C squared. That's a long-winded, that's a short, you have to actually show that this is, you can rearrange these things like that. But yeah, you can kind of understand why this would be, kind of move these triangles to fit it in. So this triangle is this triangle, but sorry, this one here kind of rotated, and they're all kind of rotated around to make this square. So, but we won't talk about that more, but that's an interesting proof of Pythagoras' theorem. Okay, so we'll move on. Yeah, so angle of elevation is the angle from the horizontal line. So, and the depression is the angle below the horizontal line. So I mentioned depression earlier, and elevation is similar to bearing, but taken from the horizontal rather than the north. Okay, so now we move on to trig. So bearings and trig are kind of friends in some sense, because whenever you have a bearing question, well, not whenever, but bearings, you want to calculate angles, and trig can help you calculate angles and lengths, and so that's why they kind of appear very much together. So yeah, trigonometric functions. So we have sine theta equals opposite over hypotenuse over h. Cos theta equals the adjacent over h. And tan theta is the opposite over the adjacent. There's a little memory thing here. So sine is so, and cosine is ka, and tangent is toa, SOHCAHTOA, and that might help you remember which one it is. A useful little thing to prove, if you guys are up for it, is to prove that sine theta plus squared plus cos theta squared equals 1. And a hint is that it's just Pythagoras' theorem, but you can check it for yourself. Okay, so now we move on to trigonometric functions. So these are the well, I think they were both trigonometric functions, but in this case we're looking at specifically the graphs. So key points: sine theta and cos theta, they both go from 0 to 1. From -1 to 1. The magnitude goes from 0 to 1. But their values go from -1 to 1. So, and you kind of expect that, because x squared plus sine squared plus cos squared equals 1. So when you graph that, you have to keep that in mind. Now, I like sine starts from 0. And cos starts from 1. So as you can see, sine goes from 0 and cos starts at 1. And basically, what I like to remember is cos goes down and sine goes up from there. So if we start from 0, you have to go up to 1, down to 0, and then like that kind of thing. And it hits 0 back at pi, or indeed 180 degrees. Cos theta hits 0 a bit quicker, hits 0 at 90. And then kind of continues along its way, and every pi they kind of hit the x-axis. So that's useful to remember. Every 180 degrees. So when you're graphing that, find your own ways in which you want to remember that, but you could just remember the diagram, or just remember which one starts where, which is what I like to do. Key points to get right when you graph is that they have to go from -1 to 1. And so your maximum values will hit that point. If you can get that right, and where they hit 0, then it doesn't matter how you draw it. You know, that's basically, it gives the right picture of what it should be. Okay, and finally this tan graph. Now this one's a bit strange. Admittedly, if it's the first time you're seeing it. And the reason, so basically, the issue is that cos becomes 0. It's sine on cos, and cos can become 0 at some points. Cos becomes 0 precisely when sine is 1 or -1. And so what you end up getting is you get a 1 on 0, which would be infinity. So you get, well, the limit. Okay, we'll just say, yeah. So it goes to infinity in both directions here. One's the positive infinity, one's the negative infinity. So I guess the useful thing to remember the shape of it, and that it happens precisely at the points where cos is 0. And it happens at 90 and -90 and 100, and 270 and -270, etc. Then you can just draw between those two, between those lines, you can draw the tan. Do you think they'll ask about drawing tan in the IGCSE?
I'm not quite sure. I've never seen, but they might.
Yeah, they might, but yeah, cool. And yeah, this guy doesn't have a bound, so it literally goes every value from R. So yeah, we kind of said that, but it's important to note that guy doesn't have a bound. Okay, now we have some sine and cosine rules. So the sine rule is so the sine rule is basically you take a side and the opposing angle. So A and the opposite angle A that looks to that side. C goes to C, etc. And then the ratios of the angle on the length are the same. So A on sine A equals B on sine B equals C on sine C. Also, one thing you could also do is, if convenient for you, you could also have sine A on A equals sine B on B equals sine C on C. I mean, you can just invert it, if that makes calculations easier. Cosine rule. So cosine rule is quite useful because it's basically like a variant of Pythag. Pythag that works when, say, your A angle is not 90. So remember, cos of 90 is when it hits 0. So when A is 90, then this guy is just 0. So you get A squared equals B squared plus C squared. And when it's not 90, well, then you start getting this extra term that describes, basically describes if the triangle is acute or if it's obtuse. That's like a measurement of that. So yeah, this is a very useful formula when you have two sides and an angle. The sine one is useful when you have, say, well, so long as you have an angle and a side that oppose each other, you can use the sine rule. But the cosine rule, you specifically need two sides and an angle between those two sides. So yeah. Now, there's also another rule that we want to remember, and it's that you can calculate area using sine. So I'll just give a little derivation here. But if I draw this perpendicular, now the area is b times height on 2, height being PQ. But PQ we can calculate using trig. So remember, sine is opposite over hypotenuse. So A times sine of C will give you PQ. And that's kind of the formula. So area is half of B times A sine C. And that kind of, in some sense, also describes to what extent the triangle is acute or obtuse, because when C is 90, this just becomes 1, and so it's just half of base times height. Okay. Workout. So is that all good, Devon? Should we talk about anything else?
That was great.
Okay, cool. Okay, so we have two triangles here, and we have to calculate some lengths. Trig will be our friend here, of course. So we have to calculate first QR. So what I do when I look at this is I just know what I have to really look at. We have to look at what we have, right? And that's what I do. So I go, okay, so I need QR. This is a side. I have a side, and an angle between. It's going to be cosine law. So we apply the cosine law. QR squared equals 150 squared plus 120 squared minus 2 times 150, sorry, no, 105 times 120 cos of 25. And we calculate that. If you guys check it for me, probably this 105 made an error in my calculation, but you know, that's the how you do it. So 150 there would be what you need, and we find QR equals 65.37. Assuming that I didn't put 150 in my calculator, 105 in my calculator instead of 150. But that's how you do it. So it's cosine law for that. Now let's look at RS. So RS, we have a length and an angle opposite to it. So yeah, we will be able to use sine law, but we not quite yet. So to apply sine law, we need almost 2 pairs of side and opposite angles. That's how we get information. So we will need to find this angle, right? We can find this angle by 180 minus 45 minus 55, which is 80 degrees. And so then this angle is 80. And so we can then apply sine law. So sine 80 on 150 is equal to sine 55 on RS. Then we multiply by RS, single out on one side, and we can solve it and get RS is 127.77 meters. Sometimes these diagrams aren't drawn to scale, but it seems like they have been. So, QR in some sense looks like, kind of half of this side here, and that's kind of what we have. And RS really does look like it's a bit less than PR, but pretty close. So, yeah, these values make sense.
In the exam, there's writing not to scale, but I deleted here so that we have more space.
Yeah, no worries. I mean,
Yeah.
For some reason, to me, it actually looks like they've drawn it pretty well, but
yeah,
definitely. Like if it says not drawn to scale, then don't let. In some sense, if you think you've done the right process, then you could use that as maybe like to make you feel better. But don't say, oh, my thing kind of looks wrong now. Looking at the diagram, don't do that because as Devan said, it's not.
Yeah, it's really not to scale.
Yeah. Okay, so now you have to calculate the area of the two triangles. So really, we know that RS is 124.77 from the last thing. So I'm using the formula I gave you guys. We have side angle, side angle. So this is just a work for sine rule. You can just calculate sine rule in both triangles. So it'd be 120 times 150, sine 25 half. Plus, so that's the area of this triangle here. So that's this expression here. And the other expression is for this area. And then we just add them and we get the answer. Oh, sorry, this should be meters squared. Units, very important. Okay. So that one's actually quite simple from B. So in some sense, if they ask you to calculate C, you would have to think about using sine rule and how you could do that. And so you would need to think, oh, I would have to find this length. Or say PS, for example. But yeah, you would have to, sometimes they can ask you not in a stepwise fashion. Okay, so we need to find the bearing from D to B. So I've drawn, so I don't think this this line was actually there. So I've drawn this line B to D. And basically, we want to find the angle from the north. So it would be 90 of whatever this angle is here. So let the angle be theta. We want to calculate what theta is. But we have basically everything. We have 350 and 450. So we've got a tan coming in. So tan of theta is the opposite over the adjacent, which is 450 on 350, which is 9 on 5. And then we apply inverse tan to find theta. And we get theta is about 52.13 degrees. And then to finalize this, we just take 90 minus 52.13, which is 47.87 degrees, and that's our answer. I probably didn't do the bearing properly. So yeah, I made the error by not doing from the north, but yeah, it would just be 90 minus that angle.
Yeah, it's okay.
Yeah. Bearing gets you, doesn't it? It's like you have to be sure it's from the north. I mean, this would be angle of elevation. So, my defense, if it was angle of elevation, then it would be good. Okay. Apologies, there was no animation, but let me just describe. So we have to calculate the distance from D to A. So we need this length, D to A. I mean, they've given us 90 degrees, so in some sense, we know what we need to do. We need to find this length and this length. So when we have a geometry diagram, it's good to label everything we're going to use. So basically, we're going to label Q as this point here, and P as this point here. Now I've extended to make a 90-degree triangle. It kind of seemed like it should be done, and so yeah, that's the reason I did it, because we want to find AQ, and that's just PC, and we want to find dq, but that's just a dc minus ap. So it makes sense to draw these lines. So we know, because this angle is 140 degrees, that 180 minus 40, 140 is 40. So this angle is 40 here. And then now we have a triangle for which we know the hypotenuse. And so we can literally calculate AP and PB. So AP is just the cosine, 400 times cos 40, because it's the adjacent. And PB is the opposite, so it's 400 sine 40. And now we can calculate what AD is. So AD by Pythagoras is the square root of AQ squared plus DQ squared. Now AQ is equal to PC is equal to 350 plus PB. So that's the thing here. And DQ is equal to DC minus QC, which is DC minus AP. And that's what we have here. And so we square it, and we evaluate this, and we get that AD is 623.86. So yeah, it was a bit of a process, especially to draw these lines here, but it almost seemed like it should be done. And so yeah, there probably are other ways of doing it as well. You know, whatever. The key was to use this angle 140 somehow, and to get a 90 degree triangle would be good. And so this is one reason why to see, because we have a north and let's say an east, and that's a 90 degree coming out. Do you have any would you draw that, Devan? Like, would that be natural to you?
I think I would. Actually, I think I would.
Yeah,
I
okay.
didn't solve it on my own.
Yeah, I know. But I'm just curious as to yeah, if that's just natural to do. Okay. So that's how you do that. That's how I would do it. If there are other ways to do it, you could also draw the 90 degree here, say, and so you know that that's just 350, and basically this 90 degree here is just like a flip of this 90 degree. So it doesn't make a difference. It's the same formula. But you just have to, yeah, this angle is not as obvious to calculate. Well, it is. You have a kind of a parallel in co-interior angles right here if we draw perpendicular. So there's many ways to do it, but the key thing is to draw perpendicular to use information from the diagram and the angles. Okay, so next question. Joe runs through the field. He runs from A to B, B to C, C to D, and D back to A. Now, of course, if this was a displacement, then he would basically go in zero, but which would be nice. But of course, it's asking for total time, so we can't do anything like that. Yeah, so we basically calculate the perimeter of where he's running. So we found dA in the previous thing. So the perimeter will be 400 plus 350 plus 450 plus 623.86, which is 1823.86 meters. Now he's going at 3 meters per second, so you know, speed equals speed. Sorry, when I put speed here, I should mean time. So speed times time equals distance, i.e. time equals distance over speed. So this should be time. So the time is the distance over the speed. And we can just double check our units. So we have meters and meters per second. The meters cancel and we get seconds. So that's always important. Dividing by 3 gives us 607.95 seconds. And so now we have to convert to minutes because they want us minutes and seconds. So 607 seconds is like 607.95 on 60 minutes, because there's 60 seconds in 1 minute. And so we get 10.13 minutes. But of course, they also want us in seconds to the nearest second. So 0.13 minutes is like 0.13 times 60 seconds, or indeed 8 seconds, roughly. So it's not 8 precisely, but it's like 7.8. But yeah, if we round up because they want near a second. Anything there to mention, Devan? Or
No, nothing.
cool. Okay. Okay, so now we move on to a bit of a different scenario with trigs. So we're looking at now graphs of the trigs. So on the axis, sketch the graph of sine x from x is 0 to 360. So of course you could just remember it. It's kind of looks like this. So as I said, the key points is to make sure that your maximum is at 1. So yeah, this point should be at 1. Sorry, I kind of missed that, but yeah, this highest point should be at 1 at 90. It should start at 0. After it hits its maximum, it goes down back to 0 at 180 degrees. And its maximum will be at 1, and it's at 180 degrees will be 0. And then it goes to -1 at 270 degrees, and then it hits 360 degrees at 0. So it kind of goes like a full loop kind of thing. And so now we're asked in part 2 to describe the symmetries of sine x. So you can see one symmetry. Sine of x seems to be the same if you draw like a horizontal line right here. Sine of x seems to be the same at x and 180 minus x. So yeah, from the graph we can see that sine of x equals sine of 180 minus x. We can also see that sine of x is negative sine of 360 minus x. So basically the point is that if you have sine of x here, the y, then the y-axis here is the negative of that. So we can like kind of flip this point across the symmetry of 180 degrees around this point, and we get this point here, that's the negative of what this y was. So that there are kind of two symmetries. And you can apply these two rules. So sine of x equals sine of 180 minus x. And if you take 360 minus 180 minus x, you get 180 plus x, and that makes it negative. So in fact, sine of x equals also negative 180, negative sine 180 plus x. So these are the symmetries I could find. It's 2 marks. Any other symmetries you would say, Devan?
Oh, yeah. There's a rotational symmetry in 180. I think that's more simple, I think. A rotational symmetry, order 2, at 180.
Okay. Yeah. Sorry. So yeah. Okay. That's sure. So you mean around 180, you rotate this guy and you get there. Is that right? It's half.
Yep.
Yeah. Okay. Yeah. So yeah, as Devan said, that's basically yeah. So if you rotate this here, you would get this identification is identified with this. So what that is telling you is that sine of 180 minus x is the negative of sine 180 plus x, which is basically this what I've said here. But as Devan said, that's one way you could also say a rotational symmetry around 180. Perfect. Okay. So now we move on to our final question, which is solve for sine x minus 1 equals 2 for x between 0 and 360. So our strategy will be to take 1 to the other side and divide by 4. We get sine of x equals 3 on 4. And now we have to solve that. Basically, the idea is that if we look at the graph, 3 on 4 is positive, and sine is positive only on the region of 0 to 180. And it's the same value when you have at some angle here and the complement of that. So we're going to just say that properly. So directly, we have sine of x is 3 on 4. We have to find the solutions. Naively, we could just apply the inverse. When we say inverse, we really mean, well, this inverse of sine is defined in a particular domain for which you don't have two solutions when you invert, because that wouldn't really make sense as a function. Imagine a function that when you put in like x and you get 2 values of x, that's a multi-value function. It's not really a function. But when you input inverse sine, you get that the answer is 48.59 degrees. However, we've just seen that there can be two solutions, and in particular, we know that sine of x equals sine of 180 minus x. So the complement is also a solution, i.e. 180 minus 48.59 is 131.41, and yeah, that's also another solution. And that's it. So I guess it is a bit tricky in some sense, but if you break it down into figuring out where sine is positive and negative, that can really help in kind of figuring out, where the solution should lie, and then just applying the symmetry kind of laws that we have for sine. Right. So wrap up. We saw a few bearing questions, a few trigonometry questions, a few area questions, so a few geometric questions, all using trig. And that's pretty neat. Trig is important to kind of master because you can get quite difficult questions with them. But they all kind of follow a process where look at what you have and then from there try to extrapolate to find an answer to whatever the problem's asking. And yeah, we also saw some functions and of tree graphs and their symmetries, and basically we finished off with a question that highlighted the fact that sine does not have a well-defined inverse, but it does on a particular domain. In particular, the domain could be like negative 90 to 90. But this is a nitpicky point. But basically what that means is that when you want to solve sine of x equals something, you could have more than one solution. And that's it. Anything more to add, Devan?
No, you've really explained everything well. That's enough.
Cool.
And so yeah, we're done. And just a small comment. Someone from the comment section was praising your animation. She really liked your animations.
Oh, thank you very much. They will get better. I haven't been having as much time recently, but I'll try to make them even better.
Yeah. I mean, you really worked hard for this, and you had a kind of hectic day, was it?
Yeah, quite a challenge, moving places and stuff, and yeah.
All right. So yeah, that's it. And so thanks everyone for watching today's episode, and thank you, Ivan, for being with us today. Don't forget to check out our Instagram page, our website, and also join our Discord server. Come talk to me or Ivan anytime. And that's it. We'll see you next Wednesday.
Thank you, everyone. See you next week.
Thank you. Goodbye.
Bye.